Let's look at linear expansivity, area expansivity, and the cubic expansivity in physics. You understand me now? So let's see. First of all, the word expansivity comes from the word expansion, where something expands. Either it increases, or it becomes wider, or it becomes deeper. Get my point? Becomes longer, it expands. Becomes wider, it expands. Becomes deeper, it also expands. Understood now? So when something becomes longer, that's linear. When something becomes wider, that's area or superficial. Area or superficial. When something becomes deeper, that is cubic or volume. So we call it cubic or volume expansivity. So something becomes longer, it's like length. Let's say an iron rod length becomes longer. Understand me now? That's linear. Understand me now? When let's say this shape now is a let's say a square, it now becomes becomes wider. That's area or superficial. When something becomes deeper, like volume. Let's say a cube, a cube, hmm, a cube becomes deeper, becomes deeper. You can see, becomes deeper. Understand me now? That's what inside. The inside becomes wider, deeper. That's cubic or volume. Hope you get that. Now becomes longer. You can say meters. That's like one dimension. Just one dimension. Becomes area, becomes wider. That's two dimension. Let's say meter here, meter here. That's meter times meter. That's meter square. Okay, you get me now. Now cubic is like 3D. 3D. That's three dimensions. Like we have length, we have breadth, and we have height. Length is longer, breadth and height. You get it now. That's three dimensions. That's meter. 1, 2, 3 is per 3. Hope you are getting the point. Very interesting and simple. So note that. Now let me explain now. Now let me start with linear expansivity. What is linear expansivity? I will define it for you. You can grab your pen and put it down. Take a pen and put it down. Linear expansivity, it has a symbol. The symbol is alpha. Area expansivity is beta. While cubic is gamma. Like if you turn your alpha, up like this, that's gamma. Understood now. So now, what's linear expansivity? Very interesting and simple. It is defined as the increase in length. Of course, like I say, expansion means increase in length. Increase in length per unit length for each degree rise in temperature of the substance, of the material. Don't worry, I will break it down. Just calm down and relax. Linear expansivity is the increase in length, because linear means something increase in length, becomes longer. Increase in length of a material per unit length. Then per each degree rise in temperature. Now let me explain to you. Part of the effect of heat on a material is that it makes a material, it makes it to expand. Either becomes longer, becomes wider, or deeper. Effect of heat on a material. You understand me now? Now let's say we have an iron rod. It can be a copper, it can be anything. Let me use just a metal. So let's say this is a metal. Let's say the length is let's say 5 centimeter for an instance. That's the length. L for length. That's metal. There's some property on it. That's how long and how hot it is. That's temperature. How hot, that's temperature. That's theta. Theta for temperature. So let's say the L1, the first length, is this. Let's say our theta 1, the first temperature, first one, initial temperature, that's theta 1. This is initial length. Let's say it is 4 degrees Celsius, for an instance. Now, when you now heat that rod, you heat it, you put it on heat, you heat the rod. Let's say it now, maybe after some hours, it now, normally it will make it to increase in length. Let's say it has increased from here, it has become longer. Hope you get the point. It has become longer this way. Let's say from 5 to, let's say 5.02 centimeter. It has increased from 5 to this. Of course, that's the second length, L2. This L1, first length, L1. This L2, second length. And you know, it has increased because you have heated it. So the temperature will increase from theta 1 to theta 2. Let's say it increased to, let's say 85 degrees Celsius. I'm just citing it as an example. You can see. So this is your L1, the first length, the first temperature. Second length become longer and it has become hotter. Becomes longer, becomes hotter. That's what we know. Now, let's say the whole thing occur for, I'm just using an example. Let's say it occur for, let's say 5 hours, for example. Okay. Let's say 3,000 minutes, that's seconds. The whole thing occur for 3,000 seconds. Seconds, for an instance. Now, you know, you can see that even after the whole 3,000 seconds, it has increased by a very small amount from 5 to 5.02. Very small amount. Understand me now? So, which means that it is not after that the whole 3,000 seconds, you know, that the whole thing increases. It has been increasing gradually, starting from 1 second, 2 seconds, gradually, maybe from 5 to 5.0001, 5.0002, 5.0003, up to that 5 points, the longer one, higher one, 5.02. That means for every rise in temperature, as the temperature is increasing, let's say from 4 to 5 by 1 Celsius, 5 to 6 Celsius, 7 Celsius, 8 Celsius, as that temperature is increasing, the length also is increasing gradually by small amount until it now become the whole length after this when you get to this 85 degrees Celsius. So those small increments, as temperature is rising by 1 degree Celsius, those increase in length, this small amount, that small amount is what we call linear expansivity. So expansivity is a gradual increment as temperature rises by 1 Celsius or 1 Kelvin. Hope you get the point. That's why from the definition, linear expansivity is the increase in length, very small increase in length per unit length for each degree rise in temperature by 1. For every degree rise in temperature, the increment in length is called linear expansivity. Interesting, right? Don't forget to subscribe to my channel to get more of this. Share my videos to your friends. Understand me now? Share it to your friend, like my video, and drop your positive comments. Don't forget that. As you are watching this, just press that subscribe button. Okay? Now, having known that, so let's now look at the formula for our linear expansivity. Let's see. Now, the formula is this. Let's see. So, of course, the symbol is alpha. Linear expansivity. So, in fact, I will give you the formula based on the definition. Is defined equals to, as the increase, that's change. Anything change means it has increased. Let's say, for an instance, you are 15 years old last year. Now, this year, you are 16, which means your change in age is 1. So, the increment. So, increase in length, L for length, per means over, per unit length for this L1, per L1. So that is the amount by which the length is increasing on this normal length before. So per unit length, then per, some will say per each degree rise in temperature. Each means 1. So the same thing also L1, then per each degree rise in temperature. Because this is like per increase in length. So this thing means as temperature increases by 1 degree, so increase per unit length, per degree rise. Rise means this change. Rise means 1 per degree rise in temperature. That's what we call linear expansivity. So this is the formula for linear expansivity. You can see change in L over L1, change in theta. So you see now that physics is not always calculation. We have the mathematical aspect. Then we have the theoretical, the understanding aspect of physics. We have to know the two to be able to understand it perfectly. So that's the formula for linear expansion. So of course, let's just work the maths. So linear equals to what? So of course, change in L means the amount by which the length changes. So that's going to be the final length, that's L2, minus the initial length, that's L1, all over L1. This is also the same thing for the temperature because of the change, that's theta 2 minus theta 1. Hope you get the point. So that's the formula for linear expansivity. You can see now. So if they give you any examples, just apply this formula. Just try to know the okay, maybe I will give you one or two examples before we move to area expansivity. You understood now? But this video is to make you to understand the concept. You understand it very well. Maybe next class I will now give you the full calculation of these three. You understand me now? But for now, I want to understand the concept, because if you know the concept, you can always remember the formula anytime, any day. Understood? Okay. So let's move to area expansivity. And of course, like I told you, what we are looking for here is just a small, we can imagine this definition is not a small amount, increase in length. You understand me now? That's what we are doing here. Expansivity. Now, before I forget, the unit of linear expansivity is what? What is the unit of linear expansivity? You can know from here. Let's say your length is in meters, meter. This is meter. All over. Length is meter. Temperature is in Kelvin. Theta in Kelvin, or you can put degrees Celsius, anyone. So what happens there? M cancels M. So our unit is what? All over Kelvin. That's all over Kelvin. So that's units of linear expansivity. Some uses this, some use this, or let's say if your temperature is degrees Celsius, you can use this. Or there's the one here from law of indices. When the K comes up, it turns to K raised to power -1, or this. And if it's degrees Celsius, degrees Celsius by what? The same -1. You can use this, or this, or this, or this for your temperature. And sometimes your temperature can also be in degree Fahrenheit. So it depends on what you have. So note it. That's the unit of a linear expansivity. Note it. Now let's go to area expansivity quickly before we continue. Let's go there. So don't forget, this class is to give you the concept, the formula, and the concept, because it will help you to solve any kind of question. So in my next class for this, we now solve, we look at the real deep mathematical aspect of it. But this is even more important, because this is the background, the foundation, and the understanding part. You understand me now? So let's see. Let's go to area expansivity. In fact, okay, let me just. Now let's go to area expansivity. Some call it area expansivity or superficial expansivity. So it can be anyone. Area expansivity or superficial expansivity. That's beta. The same pattern, just like linear expansivity. The same pattern. They follow the same pattern. So I said linear expansivity deal with how small becomes longer, while area expansivity deal with how wide. Let's assume that we have a particular metal, like a rectangular metal. You understand me now? So of course it's going to have its own length and its own breadth, or width, and its own theta 1. The first temperature. This is the first length, first breadth, the first temperature, and this area. Let's call it the first area, area 1. So the inside is the area. The first length, that's the initial length, initial breadth or width, the initial temperature, theta 1 here, theta 1. That's how hot this thing is, degrees Celsius. Why this is the initial area. Of course, your length and breadth give rise to area. Without length and breadth, there can't be area. In fact, as a matter of fact, area is taken from this. Like each box here, each one unit, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 centimeters square. That's the whole area. They add together and get the whole area. That's origin. Understand me now? So we have area 1, the first area, A1. Now let's say after we have now heated this metal, of course the area will expand, which means the length must have increased, the breadth too must have increased, which gives rise to the whole shape. Now you can see now the area has increased to A2, because the length has increased from L1 to L2, the breadth has increased from B1, it has become longer, to B2. Therefore the area 2 has increased to A2, because the temperature increases from theta 1 to theta 2 degrees Celsius. You can see. So for linear we are using L, the one we did before. For area we are using A for area. Hope you get the point. Linear for L, area for A. You understand that? So now that gives us the formula for the what's called area or superficial expanse. The same thing, they follow the same pattern. The same pattern for it. So let's say So in fact, I'm going to, okay, let me define it for you. Sorry. What is area expansivity or superficial expansivity? It's similar to linear expansivity. Just go and check on linear expansivity. Whenever you see L, you put area. That's different. L for linear, A for area. So how do you now define it now? Area expansivity is defined as the increase in area, not length again now, per unit area for each degree rise in temperature. I only remove L and my length and put area. In fact, the unit of area expansivity is still the same thing as that of linear expansivity, the same unit. Why? Let's see. And the formulas are similar. The formulas are also similar. Similar formulas. So let's see. So area expansivity is beta. Area expansivity is defined just like this as the increase. Now I'm not using N number, I'm using A in area per unit what area A1. You can see. Now per each degree rise in temperature. Same thing. I'm going to have what? Change means the second area minus first area. That's change in area all over area 1. This one is what? Theta 2 minus theta. You can see that's the formula for area expansivity. And of course, the unit is still this. Why? Because by the time area is in meter square, that's area. I told you the inside. All over area is still meter square times your temperature is still Kelvin. So your meter square still cancel meter square. So we still have per Kelvin, just like linear expansivity. Hope you get the point. Just like linear expansivity. So the same thing goes for area expansivity. Same thing. Understood? Now you have to note this. Like linear is one dimension, area is two dimension. That's why what makes that gives us the relationship between area expansivity and linear expansivity. This is area expansivity is always twice. See now, linear is 1, area is 1, 2, like area. So area expansivity is twice of linear expansivity. So note this. By the time we get to our next class, we use all this formula. Understood now? So area expansivity equals 2 times of linear expansivity. And area expansivity has the same unit as linear expansivity. That's the unit of what? Per Kelvin or per degree Celsius. So I will stop here for now. So in my next class, I will begin with volume expansivity or what? Cubic expansivity. Understood? Volume or cubic, and then I will take the mathematical aspect of all this area, because volume expansivity can be we have apparent cubic expansivity. We have the expansion, that expansivity of the vessel itself. Then we have real cubic expansivity. We have a 3, understood now. So we take it in the next class, and then we're going to take general calculations concerning what are general expansivity, linear expansivity, area expansivity, and volume expansivity. Hope you have gotten the scope behind at least today we did linear expansivity and area expansivity. Understood? So once again, welcome to Mr. Brown's online class. Don't forget to like my video, drop your positive comments, share my video, and as you are watching it, hit that subscribe button in order to get more of my video. Once again, thank you. Love you.